Okay, so today we are going to pick up where we left off last class. I guess that's fairly obvious. So we are working through lecture set number 2. We're very close to being finished with this lecture set. We just have one more example left of a one sample t-test. Make sure this looks the same to me. Awesome. So we have one example left illustrating a one sample t-test, and then we're going to start lecture set number 3. Lecture set number 3 is about two sample hypothesis tests. And in particular, we are going to focus on two sample t-tests. And we're going to look at the two sample t-test in two different situations. In lecture set number 2, we focused on one sample inference. So the first part of lecture set number 2 discussed confidence intervals when you were interested in studying a single population mean and you have a single sample of information. And we looked at the construction of confidence intervals from two different points of view: when sigma was known and when sigma was known and when sigma was unknown. We took the same 2 points of view with the hypothesis tests. So the first 2 illustrations of hypothesis tests in lecture set number 2 were focused on how you would run the test when sigma was known. So basically using a z-score and using the standard normal table to create to find your conclusion about the test. The last 2 examples, so the one we finished off with last class and the one we're going to start with today, they are focused on the same goal, but in this case, sigma is unknown. And as a result, we have to use a student t distribution. All right, so as a reminder, when we're working through the hypothesis test, I will show you how to construct your conclusion about said hypothesis test using both the p-value approach and the critical value approach, but you do not need to do both on assignments and tests. Most often you will have a choice of which one you would like to use, and in some situations you might be told to take a particular approach if we want to test your skill at that particular approach. All right, so in the second illustration on slide 35, we have, according to Communications Industry Forecast and Report, the average person watched 4.55 hours of television per day in 2005. In 2015, the average amount of time spent watching TV by the individuals in SRS of size 20 was 4.76 hours, with a standard deviation of 2.297 hours. At the 10% significance level, do the data provide sufficient evidence to conclude that the amount of time spent watching TV per day in 2015 is different from the average reported in 2005? Okay, so let's see how much room. Okay, give myself a full page. All right, so let's start off just by making note of a few different items here. There's quite a bit of information in this question. So first off, we're told the average person watched 4.55 hours in 2005. And we want to run a test to determine if there is evidence that the amount of television watched per day in 2015 is different from that in 2005. So this would mean that our mu0 is going to be 4.55. We are also told that in 2015, we have an SRS of size 20, and the average amount was 4.76 hours. So this is telling us a few things. It's telling us that X bar is 4.76. It's telling us that the sample size is equal to 20. And then we are told with a standard deviation of 2.977. Okay, so this is telling us that the standard deviation of that simple random sample is 2.2977. So that means that we have S is equal to 2.297. All right, at the 10% significance level, do the data provide evidence of a difference? So this would mean that alpha is going to be 0.1. All right, let's check the assumptions on this slide, and then we'll run through the test on the second slide. So we have assumptions. So the first assumption is a simple random sample. We'll just give this a little check mark because you can tell in the question it says that we have an SRS. So that is sufficient. Okay, the second assumption is normality. So we have a normal QQ plot or a normal probability plot given on slide 35. We can see here that for the most part, the observations in the sample appear to follow that linear pattern that we are looking for. There's a little bit of activity in the upper parts or in the upper tail. So this circled part here, actually, it's really just this observation here is a bit far off the line, which would indicate a little, maybe a bit of an outlier or an outlying point potentially. But for the most part, the bulk of the observations appear to follow that straight line pattern. So this would give us evidence that the population of interest is normally distributed. So we can say here, since sampled values form a linear relationship with normal quantiles, we have evidence of normality. All right, a little tight on space, but what I wrote there was, since sampled values form a linear relationship with normal quantiles, we have evidence of normality. So effectively what I mean is there is evidence that the variable is approximately normal because the QQ plot shows a linear pattern. That would be a similar explanation of the same result. But either way, what we have here are the SRS assumption being met and the normal and evidence of normality of the population, which are the two things we need for our hypothesis test. All right, so now we'll run through the steps of the test. Okay, so we're testing if there's a difference between the means, the mean in 2015 compared to the mean in 2005. We're treating this as a single sample test. So we're going to have mu is equal to 4.55 versus the alternative that mu is different from 4.55. Right. As stated before, alpha is equal to 0.01. Okay, on step 3, we're going to compute our test statistic. Again, since we do not have the population standard deviation, this is going to be a t value. So we have t is equal to x bar minus mu 0 divided by s over the square root of n. So that's going to be 4.76 minus 4.55 divided by 2.297 over the square root of 20. And this is going to give us 0.409. All right. Okay, so on the fourth step, we can take the critical value approach or the p-value approach. This is our evidence gathering step. So what we are looking for here is evidence to support or to reject the null hypothesis. So if we were to start with the critical value approach, we would start by sketching out our t-curve. So we might have something that looks like this. All right, so here is a student t-curve centered at 0. Okay, so we are going to have a critical value of equal magnitude, or two critical values of equal magnitude in the upper and lower tail of the curve. So it's a two-tailed test, which means that we have to divide alpha by 2. So we're going to have t alpha over 2, comma, n minus 1 is t 0.05, comma 19. Right. Okay, so now what we have to do is go to our t-table and we find the critical value by comparing the degrees of freedom with that significance level. All right, so here is our student t-table. So we have alpha 0.05. We have 19 degrees of freedom. That gives us a t-value or a critical value of 1.729. Okay. All right, and the lower tail, we're going to have the same value, just in a negative. So we can write negative t 0.0519 is equal to negative 1.729. All right. And now we can just place our test statistic. We can see that the test statistic in this case is not going to be inside the rejection region. So this value here is t equals 0.409. All right. Okay, so that would be our critical value approach. And we can see from the critical value approach that the test statistic does not get into either rejection region. So as a result, we are not going to reject the null hypothesis based off of this test statistic. Any questions? All right. Okay, so we can also take the p-value approach. Okay, so the starting point is the same. We just begin by sketching our student t-curve. Now what we're going to do is mark down where the test statistic is located. So that's going to be, let's say here. And because it's a two-tailed test, we'll have the negative as well of roughly giving the same size regions, trying to sketch those to be as equal as I can. So we have t is equal to 0.409. And in the lower tail, we have negative t is equal to 0.409. So our p-value in this case is going to be the two regions that are less than negative 0.409 and greater than 0.409. All right. Okay, so what we have to do now is find an expression for the p-value. So the first thing that we can do is write down what the p-value would be in terms of these green shaded areas underneath the student t-curve. So we're going to have the p-value is equal to the probability that t is less than negative 0.409 plus the probability that t exceeds. Okay. If I can just write that a little bit cleaner. Okay, so because those regions are the exact same size, this is equivalent to saying that the p-value is 2 times the probability that t exceeds 0.409. Right, so this would be the same expression. So now what we can do is we go to our t table and we are going to isolate the degree of freedom line that's of interest to us. Okay, so we have 19 degrees of freedom in this case. And the next thing that we do is we move across this line and we look for where that t value is going to fit in. So the test statistic that we computed on step 3. Okay, in this case, we don't have to look very far because we can see that 0.409 is going to be smaller than the very first value listed on this degree of freedom line. So 0.409 comes before 1.328. This is telling us that the area to the left of 0.409 must exceed 0.10. So from the t table, we have learned that if your t value is 0.409, the area to its right, will be greater than 0.1. So we can say, since the probability that t exceeds 0.409 is greater than 0.1, then the p-value must be greater than 2 times 0.1. So the p-value is greater than 0.2. Right? So that would be another illustration of the p-value approach using the student t-table. And in this case, it's a two-sided test, which is why we have this 2 times multiplier here and here. Any questions? Okay. All right, well, if you're still wondering about the p-value approach, even after seeing these first two illustrations, we will see more examples of it using the student t-table in lecture set 3. And then we will continue to see examples of the p-value approach throughout the course using a variety of different tables. So it is something that we will get, you'll get a fair amount of practice with going forward. Okay, on step 5, we simply have to make a decision about the null. Again, the p-value and the critical value approach are going to agree here. So if we take the critical value approach, we can see that the test stat is not in rejection region, do not reject H0. If we take the p-value approach, we can say the p-value is greater than 0.2. 0.2 is bigger than 0.1. Therefore, the p-value is bigger than alpha. It's greater than alpha. So do not reject H0. All right, and then all that's left to do is conclude. So we can say at the 10% significance level, the data do not provide sufficient evidence to suggest that the average amount of TV watched in 2015 is different from that watched in 2005. Okay, so I have at the 10% significance level, sorry, one sec. Okay, so I'll just read this real quick and then I'll answer the question. At the 10% significance level, the data do not provide sufficient evidence to suggest that the average amount of TV watched in 2015 is different from that watched in 2005. Question. So the question is, for the p-value approach, you do not reject H0 if it falls within the green area. So with the p-value approach, the green shaded area represents the p-value. So these green shaded tails are actually what the p-value would look like visually. With the p-value approach, we don't consider the green shaded parts to be rejection regions like they are in the critical value approach. With the p-value approach, we strictly compare the value of the p-value to the significance level, and that's how we make our decision about H0. So it's only with the rejection or with the critical value approach that you would compare the test statistic to the critical value and determine if that gives you evidence for or against the null. With the p-value approach, you always compare the p-value to alpha directly to determine if you reject or do not reject the null. Does that make sense? Okay, cool. Any other questions? All right. Yesterday I went outside and I scraped all the ice off of our driveway and the sidewalk in front of our house. And we live on a corner lot, so it's like a freaking annoying sidewalk. And then the second I finished, it snowed. It was this winter has been it's been tough to keep up this winter. Anyways, okay, so that brings us to the end of lecture set 2. Lecture set 2 again is a review of one sample inference. So we're still reviewing material from Stat 151. And when we talk about one sample inference, we talk about techniques for making a decision about the value of a single population mean. You can run one sample inference in different ways. It doesn't always have to be about a population mean, but in this course, we focus on the population mean. So the techniques that we studied in lecture set number 2 were all for the same value. The major difference was the confidence interval versus hypothesis test construction, and of course, the presence, or rather, whether or not sigma is known, because that changes the value of the test statistic. All right, so at the end of lecture set number 2, there is one more example of a student of a one sample t-test for you to work on as extra practice. We are now going to start lecture set number 3. Lecture set number 3 is still focused on review from Stat 151. In this lecture set, we are going to be reviewing 2 sample inference. So at the beginning of the class, I had said that these are going to focus on hypothesis tests. While that is true or not entirely incorrect, we are also going to talk about confidence intervals. So again, when we say inference, we refer to the 1 sample and the 2 sample cases. All right. In this lecture set, we are going to focus on t-tests, or using the student t-distribution in our hypothesis testing structures. So we are not going to look at the z-test for 2 samples or for 2 population means in detail. This is because most often you don't have the population variances anyway, so we usually are only using sample values. So instead of looking at the z versus the t, we are going to look at t, or 2 sample t-tests under 2 different assumptions: the independence assumption and the lack of independence assumption, if you will. So we're going to look at 2 different types of 2 sample inferential procedures based off the student t distribution. So in the previous lecture set, we reviewed 1 sample inference. So we wanted to make a statement about a single population mean. In this lecture set, we are taking a natural extension, and we are now looking at hypothesis tests and confidence intervals for 2 population means. When we form our inferential procedures for 2 population means, we focus on the difference between the population means. So that is, we don't treat them separately. We compare them by subtracting one from the other. So our confidence intervals and our hypothesis tests in this lecture set will be focused on the quantity mu1 minus mu2. Okay. In lecture set number 2, where we reviewed one sample inferential procedures. The confidence interval and the hypothesis test were constructed using the sampling distribution of the sample mean. So basically, if you think about the form of the test statistic for either the Z or the T tests. In the case of the Z test, we had X bar minus mu over sigma divided by the square root of n. So you can see here that what a test statistic actually is just a standardization of X bar. And you standardize X bar using the parameters of the sampling distribution of the sample mean. All right. Now, we were also able to do certain things like say, if our sample size is large enough, the central limit theorem tells us that X bar is approximately normal. If X bar is normal, or if the population is normal, but we don't have sigma, then we can say that the test statistic is a student T distribution. In order for us to conduct inference about mu1 minus mu2, we have to know similar results for X bar 1 minus X bar 2. So effectively, what I'm trying to say is when we build these two sample inferential procedures, we take the idea from the one sample case and we just try and put it into the two sample framework. Okay. The first style of hypothesis test that we are going to look at is for independent samples. So what I mean here is I have population 1 and I have population 2, and the information from those populations, so the samples that I collect, are not related to each other. So examples of independent samples would be male versus female populations. The sample that I take from the males is going to be independent of the sample that I take from the females. When we are running hypothesis tests about independent samples, we can show that given the population variances are not equal, which is something we will assume throughout this class, the mean of the sample mean difference is mu1 minus mu2, and the standard deviation of the sample mean difference is given by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay. So this is going to be the mean of the sample mean difference. And then this part here is going to be the standard deviation of the sample mean difference. So essentially, the results that we have in the two sample case are very similar to the results, standard deviation, are very similar to the results that we have in the one sample case. So effectively what we're going to do is run the hypothesis test in the exact same way we did before, except on step 3, we're just going to have a slightly different test statistic to take into account that we now have two samples of information, and those two samples of information have a difference that has a different mean and a different standard deviation. In terms of normality, since normally distributed random variables are additive, if x bar 1 and x bar 2 are normal, then their difference is also normal. Further, if we can apply the central limit theorem to each sample separately, and if both samples are greater than 30, then we can say that the difference is approximately normal based off the CLT. So the nice thing about these two sample procedures is that they work in pretty much the exact same way as the one sample procedures. It's just a slightly different formula on step 3 of the hypothesis test. There's a slightly different degree of freedom consideration, which I'll talk about momentarily. And when we're doing our assumptions, we have to just do them for both populations separately. So effectively the same set of assumptions that we had in lecture set number 2 in the one sample case, we're just splitting it across both populations now. All right, so just like before, what we can say is if we have the population variances for each population and we standardize x bar 1 minus x bar 2 using mu1 minus mu2 and the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, we have a z-score. If we replace sigma 1 squared and sigma 2 squared with the standard deviations from the sample or the variances from the samples, we now have a student t random variable. The degree of freedom for this particular hypothesis test, so using the test statistics shown in equation 2, is given in equation 3. So you can see here that the degree of freedom approximation for this test is actually quite cumbersome to compute. This formula is what is going to be used in SPSS. Okay, so any software program is going to compute the degree of freedom using equation 3 when you are running an independent 2-sample test. In lecture, we're not going to use this degree of freedom formula because, again, the approach it's quite cumbersome to compute this. It's quite a bit of additional work. So what we are going to do instead is simply take oh, there it is. So what we are going to do instead is simply take the smaller of the 2 sample sizes minus 1. And I'll give a formal note about this in 2 slides. So just for comparison's sake, though, remember that this formula is how software like SPSS computes the degree of freedom for your independent 2-sample tests. So when you're running your 2-sample test in SPSS and you look at the degree of freedom and say, well, that's not either sample size minus 1, it's because that's not how they compute DF in those situations because they have the computer to do the calculation for you. As I had mentioned before, the assumptions of our 2-sample approaches mimic the assumptions of our 1-sample approaches. So we require now that we have independent simple random samples. So basically we have a simple random sample for population 1, we have a simple random sample from population 2, and those samples are not related to each other. So independence just means no overlap. We require that each population is normally distributed, or we have sample sizes large enough that the central limit theorem would take over. And we can say that one of the assumptions of the t-test, we can say that the variances are not equal in this particular situation. But this is going to be an assumption that we use throughout our review. So we're not reviewing the case where we have equal variances in this particular class. Right. So if we want to construct a confidence interval for mu1 minus mu2, it's going to be the same 3-step process that we saw in lecture set number 2. The only difference is how we actually compute the interval. We now have our formula shown in step 2, which basically are just adapted to take in information from each population separately. And you'll notice here that I have the official note on DF. All right, so this is just saying that in lecture and on the lecture assignments, we will take the minimum of the sample sizes and subtract 1 as our degree of freedom for 2-sample tests. Well, independent 2-sample tests. Okay. Any questions so far? All right. Okay, similarly, if we want to run a hypothesis test about the population mean difference, this is going to be done using the same 6 steps that we saw in lecture sets 1 and 2. Everything works in the same way, except that we have a different set of null and alternative hypotheses. I'm going to review those momentarily. And on step 3, again, we have a test statistic that's been adapted to include both samples of information. When we're running 2 sample tests, our hypotheses are based off of effectively comparing the population means. You can also think of these as being the difference in the same 3 situations that we saw before. So we have our 2-tailed test, our upper tail test, and our lower tail test. When we are formulating these hypothesis tests, sometimes it's also easy to think of these as direct comparisons. So each of these tests can be written in a different way that means the exact same thing. Okay, so for example, our 2-tailed test is the same thing as mu1 equals mu2 versus HA mu1 not equal to mu2. Right, so a lot of the time the phrasing of these problems is going to be, is there evidence that the first population mean is different from the second population mean? Or is there evidence that the first population mean is smaller than the second population mean? This kind of idea. In those situations, it's fine to actually express the null and alternative directly in terms of that kind of description, which is what the red or what the hypotheses in red are illustrating. But the nice thing about the first approach that's typed out is you can see directly the value that's going to be used in the test statistic. So essentially, we have 2 different ways of writing the same hypothesis test. One test shows you direct comparison of mu1 to mu2. The other test shows you the value 0, which is the value that's usually included in the test statistic. And I'll show you an example of this momentarily. Okay, for our upper-tailed and lower-tailed tests, we have the same idea. Notice that the upper tail test refers to the situation that mu1 is greater than mu2. Okay, so the upper tail and the lower tail tests are always with respect to mu1. So an upper tail test is mu1 bigger than mu2. A lower tail test is mu1 less than mu2. All right, and then here we have direction is determined with respect to mu1. Okay, so when we specify upper tail or lower tail, it's with respect to mu1. Any questions? All right. So we're going to look at an example now of running a two sample inference. So we're going to look at the confidence interval and the hypothesis test. And then we're going to compare the results. So we're going to talk about the relationship between the two. All right, so we have here several neurosurgeons wanted to determine whether a dynamic system reduced the number of acute post-operative days in hospital relative to a static system. So basically what this question is asking is there evidence that you spend less time after operation in the that you spend less time in the hospital after you have an operation on one system versus the other? So we're looking for a reduction in amount of time spent in hospital after a particular procedure. So at the 5% level, did the data provide sufficient evidence to conclude that the mean number of acute post-operative days in hospital is smaller with the dynamic system than with the static system? Part B, construct a 90% interval for the difference. Part C, compare the results. All right. So on the second slide, for the same questions, we have the following plots. So you can see that we have two normal probability plots, and then we have two sets of box plots. All right. So the first thing we can do is visually assess these normal probability plots. So basically what we're trying to do here is draw a straight line through the middle of the plot. And at the same time that we draw this line, we are then going to use the box plots to help us aid our description. Now, looking at the box plot for the dynamic system, you can see here that the spread, at least the size of the box, the spread of the two limits from the box, and then the spread of the outlying points from the box is all roughly even. Okay, so we have distances between markers in box plots are even. Issue is that, sorry, I'm just going to move this. Even. Okay, and that's not so much an issue, except we can say here, however, Q1 is equal to Q2. All right, so the median is equal to the first quartile in this box. However, we can, this actually makes sense though, because if you look at the normal probability plot, you can see, or if you look at the normal probability plot, or if you look at the original table of values, you can see that we have 1, 2, 3, 4, 5, 6, 7 people that have all spent 7 days in hospital after surgery. Okay. Okay. So The point that I'm trying to make with this, with the dynamic plots, is that for the most part, the data actually looks pretty symmetric. The median being equal to Q1 is due to repetition in the data set. So it's difficult to say if we had a larger sample size, the expectation would be that this is probably going to normalize around, around 7 days in the hospital, or it's going to become symmetric around 7 days in the hospital. And that QQ plot is not too far off from being linear. It's just that all that repetition makes it look a little bit strange. So we might be okay with the dynamic system in terms of the normality assumption. So the repetition masks the shape of distribution would expect a symmetric shape if sample size increased. Okay. On the other hand, when we look at the static system, in this situation, what we get is evidence of a right skewness. Okay, so here we have evidence of right skewness. Okay, so you can see that from the box plot, we have a lot of compact information on the lower in the lower tail. So the lower limit, Q1 and Q2 are quite close together, and then the box plot elongates and the distances get greater between Q3 and the upper limit. So this box plot here is illustrating right skewness. So given that the box plot is actually showing us right skewness, that indicates that this relationship here, while it doesn't look terrible when you put the red line down, is actually probably more of a curvature that would look like this. Okay, so given box plot, more likely the normal probability plot is showing a nonlinear relationship. Okay. Okay, so in the first situation, we could probably get away with, or for the dynamic system, we could probably get away with arguing that this is a approximately normal variable. And, given if we collected more information, my expectation would be that things are going to start to average around 7 days, and you're probably going to see more of a symmetrical relationship. But with the static system, we only have the 6 observations, but the box plot here is clearly a right skewed shape. And that implies that what we're seeing in the normal QQ plot is actually curvature. So therefore, for the static system, it's probably not realistic to assume that the variable of interest is approximately normal. Okay, so in this situation, we'll give our little assessment of the assumptions. We'll run through the test and hypothesis, the test and the confidence interval for illustrative purposes. But really at the end of this, the results are probably not going to be reliable, and we're going to need to use a different type of test for this data. Okay, so with that being said, So we have our assumptions here. So we have the dynamic SRS, and then normality. Okay, so the other issue is in terms of the simple random sample collection, we have no, or assumption, we don't know, because there isn't enough information given to us in the problem to actually determine where the information is coming from. We know that this data is based off of people that have just had surgery that are coming out of the hospital ward. So it might just be the first 20 people that they collected. It might, it might just be information over the last year of 6 people that did this approach and 14 that did the other approach. We don't know. So here we would have to put a question mark. And here we can say, can assume given plots. Okay, and then for the static system, so we don't know again. And then we can say no evidence of normality given curvature in normal. Right. Okay, so we will run through okay. So we'll complete the hypothesis test and confidence interval for illustration, but we likely need another type of test. And we're going to learn about another type of test that we can use in this situation later in the course. So we'll come back to this example later on and say, okay, do you remember this situation that we ran into? Well, here's another way that we could handle this. All right, so step 1. Give myself lots of room here, right? Yes, okay, awesome. Okay, so we want to know at the 5% level, do the data provide evidence that the mean number of acute days in hospital is smaller with the dynamic system than with the static system? Okay, so we're going to have here H0 mu dynamic is greater than or equal to mu static versus HA mu dynamic is less than mu static. So remember what I said before, the direction of our test is always with respect to the first population. So I'm effectively declaring that the dynamic system is going to be the first population here, and I'm rating my alternative as mu D less than mu S. So I'm going to run a lower tail test in this illustration. And then just as a reminder, this is equivalent to H0 mu D minus mu S greater than or equal to 0 versus mu D minus mu S less than 0. Okay, so this is the same test. Okay, on step 2, we have our significance level. Alpha equals 0.05. On step 3, we have our test statistic. So we have t is equal to x bar 1 minus x bar 2 minus mu1 minus mu2 divided by the square root s1 squared over n1 plus s2 squared over n2. Okay, so now we're going to start subbing in. So we have 7.36 minus 10.50 minus 0. Okay, so notice here I have the 0 quantity. That comes from this expression of the null and alternative. Okay, sorry. So the question, okay, I'll go back to this question. So would you prefer to see us assign the two distributions to x bar 1 and x bar 2? No, I don't care. As long as you run the test, it might be easier to do that to understand the direction that you're testing in. But as long as you set the test up and test in the right tail, it doesn't matter if you assign them to 1 and to 2. Does that make sense? Okay. Okay, so you can see in the test statistic formula here, I have a 0 where mu1 minus mu2 was. That 0 is coming from the expression that I have written in red in step 1. So that's why this expression of the null and alternative can be useful, because you can see directly where the value is coming from. Whereas the expression written in black is a more straightforward interpretation of the problem. So they both have benefits. One of them exactly represents what you're testing. The other one is kind of a reminder of, oh, I have to use 0 here in my test statistic. Okay, now we're going to sub in. So we're going to have 1.22 squared divided by 14 plus 4.59 squared divided by 6. Okay, and this is going to give us negative 1.651. Okay, and make sure, just as a reminder, when you are doing these type of calculations, you're going to want to do the two smaller fractions first, add them together, square root that, and then divide. So just make sure that you follow order of operations when you're working through these type of problems. It's very easy to make a mistake if you don't take the square root of the bottom part first. So you just want to make sure that you're following bed mass essentially when you are working through this process. All right, from this point on, the hypothesis test is exactly as it was in the one sample case. So these last 3 steps are going to be exactly the same as they were when we first started lecture this morning. So before I write down the critical value and p-value approach, I'll just make a note of the degree of freedom here. So our degree of freedom is going to be the minimum of n d minus 1 versus n s minus 1. Okay. And then I guess I should be consistent following that question, and given that I wrote 1s and 2s everywhere in the test statistic formula. So I'll just slide this part down, and then I'll just make a note. X bar 1, S1, N1 are dynamic. X bar 2, S2, N2 are static. Okay, so just for clarity there. All right, so our degree of freedom is going to be the minimum of 14 minus 1 versus 6 minus 1. So that's going to be 5. So 13 versus 5, the smaller value is 5. So our DF is going to be 5 in this case. All right, so if we take our critical value approach, okay, we're centered at 0. So we're going to have a t value on alpha over 2 comma degree of freedom. And then we'll have the negative of the same value. So this is going to be a t on 0.025 and 5. Oh, sorry, 0.05 and 5. No, at the 5% significance level. Oh, it's a one-tail test. Wow, Brian. And it's a lower tail test too. Okay, sorry about that. Got a little ahead of myself. Okay, so we are running a lower tail test at the 5% significance level. So we are going to have a test statistic or a critical value, negative t alpha degree of freedom. So we don't divide by 2 here because the it's a one-tail test. So we're putting all of the area into the lower tail. Sorry, Damara, does that change the hypothesis at all? Does what change the hypothesis? No, it's a one-tail test by definition. So we have mu d less than mu s. That is a one-tail test. Sorry, I don't know what happened there. All right. So this is going to be negative t 0.05 and 5. All right. So we go to our t table. We're going to compare, or we're going to match 0.5 to 5, 2.015. Okay, so our critical value for this test is going to be negative 2.015. All right. And then our test statistic on step 3 was negative 1.651. So that's going to be about here. So you can see that our test statistic is not into the rejection region. So based off the critical value, we will not reject. All right. If we take our p-value approach, okay, so we mark down where our test statistic is. All right? So in this situation, the p-value is the area to the left of the test statistic because it's a lower tail test. So since it's a lower tail test, we want the area below our test stat. So here what we could say is, or we can write the p-value is the probability t is less than negative 1.651. Okay. And then what we have to do is find an expression for the probability that a t-value is less than negative 1.651. So we can say, since the probability of t is less than negative 1.651. So we go back to our t table here. We select our degree of freedom line, which is 5. And we're using the same process from before. So we're going to scroll across this line and we're looking for 1.651. Now, I realize that the test statistic is negative 1.651, but since both tails are symmetric, so they're the same in terms of how much area is to their left or right given a particular value, we can just treat the negative as a positive. So in general, whenever you're using the t table, you can always just treat the value as a positive number. Okay, so what we are doing is we are looking for positive 1.651. You can see here that 1.651 is between 1.476 and 2.015. Okay, so our test statistic is between 1.476 and 2.015. So that means that the area of interest to us is going to be between 0.1 and 0.05. So we can write since 0.1 is greater than the probability that a t-value is less than negative 1.651 is greater than 0.05, then 0.1 is greater than the p-value is greater than 0.05. Okay, so what we have found here is that the p-value, so the size of this green shaded part, is between 0.05 and 0.01. Okay, so therefore bigger than 0.05 because anything in this range is bigger than 0.05. Any questions? All right, assuming there's no questions, and if there are, I'll still answer them. We can now make our decision. So following from before, the way that we make a decision does not change. So if we take the critical value approach, we can see test statistic is not in the rejection region, so do not reject. So I'll just say do not reject since test statistic outside rejection region. If we take the p-value approach, the same thing. So we say do not reject since p-value is greater than alpha. I want to make sure yeah. Okay. Okay, and then all we have left to do is conclude, so we can say at the 5% significance level, the data do not provide sufficient evidence to suggest that the mean number of post-operative days spent in hospital post. The mean number of, I was going to write post-operative again. The mean number of post-operative days spent in hospital is reduced on the dynamic system. Okay, so we have at the 5% significance level, the data do not provide sufficient evidence to suggest that the mean number of post-operative days in hospital is reduced on the dynamic system. All right. Okay. All right, so I'll wrap it up there for today. On Thursday, we will go through the confidence interval construction for the same example, and then we will compare the results of the confidence interval and the hypothesis test. Following that, we will look at illustrations of the two sample paired t-test. So that's the t-test for dependent samples. And then following that, if there's time, which I think there will be, we'll start lecture set number 4, which is technically review, but most of the material in it will probably be fresh, and it's going to discuss one-way ANOVA. Okay, so I have office hours tomorrow. You have a lab assignment due Friday. I believe the first mini project is due Friday as well, or due Monday. It's one of the two. So those can be emailed to me directly. And we will have lecture again on Thursday, and then our next lecture assignment is due the following Friday. Okay, so if I'll hang around and answer any questions if there are any. I know there's 2 in there. And then I'll talk to you guys Thursday otherwise. Okay, I'll answer the second one first, actually, just before people take off. Darby, are we going back in person after the 21st or still online? So on Thursday last week, the president sent out an email. You should have seen the email. It was sent through the student system. We're staying online until February 25th, I believe, which is the Monday after reading week. Okay. I'll send an official announcement after. I assume that everyone would have saw that. Brendan, will the critical value approach and p-value approach always produce the same conclusion? Yes, always, no matter what. Yeah, makes sense. Yeah, so we're not going to have any in person until at least the 25th of February, as of right now. Cool. No problem. No problem. See you. Goodbye.